Welcome back to the Foundry by Forge College. Man, I am so incredibly excited for today's explainer because we are finally at the point where all our hard work pays off. Think of today as the moment we get to decode the ultimate engineering schematic. In our previous explainer, we went through the gritty process of data collection and practical integration. We built the test harness, ran the scenarios, and gathered our measurements. But now, we need to analyze those results and actually build a persuasive scalability demonstration. You know, I absolutely love this analogy, mostly because it's just painfully true. Right now, that CSV data we gathered from our Solana test runs is basically a shoebox overflowing with messy, crumpled receipts. We've got warm-up spikes, chaotic network logs, dropped packets, and transient noise. You literally can't just hand a raw log file to a stakeholder or a project lead and expect them to give you a standing ovation. Before it becomes actual, undeniable proof of Turbine's efficiency, this data needs some serious refining. Okay. Let's just quickly orient ourselves in the overarching structure of our capstone project. We've already covered the advanced Solana concepts, we've explored Turbine's architecture, and we just wrapped up data collection. Right now, we are squarely on step 4, analyze results. This is the crucial bridge that's going to perfectly set us up for our final capstone assembly in our next explainer. All right, let's dive into this. Today, we're looking at a 5-part blueprint. From data to evidence, the magic of normalization, our 7-step workflow, building tables and charts, and finally, 3 rules for proof. Let's get to it. Starting off with section 1, from data to evidence, or as I like to call it, organizing the mess. So, we're really shifting our mindset here. We're intentionally crafting a scalable narrative. The crucial thing to understand is the vast, and I mean vast, difference between raw data and actual evidence. Raw data, it's noisy. It's full of those weird startup anomalies and teardown artifacts. It literally just tells you what happened in this chaotic vacuum. But evidence? Evidence is normalized. It's contextualized. It doesn't just say what happened. It actually proves how and why it matters. Which brings us to section 2, the magic of normalization. Leveling the playing field. Now this right here is absolutely crucial. It's the most critical mathematical step to make sure we're actually comparing apples to apples. Enter the steady state window. Think of it like, well, like starting your car on a freezing winter morning. For that first minute, the engine's sputtering, the RPMs are jumping all over the place, it's totally chaotic. You wouldn't measure the car's fuel efficiency right then, right? No way. You wait until you're cruising smoothly down the highway. Our steady-state window intentionally excludes all those chaotic warm-up and cool-down phases, so we're only capturing the system's smooth, sustained capacity. So let's look at a typical 600-second test run. Those first 60 seconds, that's just the system spinning up, allocating memory, establishing connections. We just throw that data out. Honestly, it's garbage for our purposes. But from second 60 to second 420, boom, we hit our steady state. This is the goldmine right here, our perfect, normalized analytical sweet spot. And then that last block is the cooldown phase, which, again, we just ignore. By consistently pulling only from that 60 to 420-second window across all our tests, our comparisons become completely bulletproof. All right, moving on to section 3, the 7-step workflow, processing the blueprint. So we know what data we want, but how do we actually extract it consistently? Well, we use a repeatable Python-based workflow. That way, anyone could rerun this and get the exact same undeniable results. The first 3 steps are really just our initial sorting and cleaning phase. First up, we reproduce our metadata context so we know exactly what run parameters we're looking at. Second, we pre-process and clean the data, parsing timestamps into a uniform format and, you guessed it, dropping those warm-up intervals we just talked about. Third, we aggregate the metrics. We group the runs by message size and concurrency and compute our steady-state aggregates, stuff like mean throughput, median latency, and, crucially, our bootstrap confidence intervals, so we can clearly state our uncertainty ranges. Okay, so now we take those cleaned parts and assemble them into a beautiful, readable format. Step 4 is creating the canonical comparison table, literally putting our baseline and turbine metrics side by side. Step 5 is visualization. This is where we generate those sweet time series throughputs and latency distributions using tools like Seaborn and Matplotlib. And step 6, validating anomalies. If there's some weird spike in your chart, we cross-check it against the raw logs to actually explain it. We definitely don't just sweep it under the rug like dust. And finally, step 7, package your artifacts. You're going to commit your comparison table CSV, save your visuals in both PNG for quick viewing and SVG for that crisp vector scaling, include the pre-processing scripts, and write a really clear analysis README. Guys, I literally cannot stress enough how important this phase is. These packaged files are the exact deliverables you're going to need for the final capstone assembly. If you don't package them properly right here, you are going to be scrambling in the next phase for sure. Next up, Section 4, building tables and charts. This is all about visualizing Turbine's power. Now what's really interesting here is we finally get to see the actual visual outputs of those Python scripts. This table matrix, it's the absolute core of your evidence. Just look at how it's structured. We've got our metrics down the side, throughput, latency, peak bandwidth. Then we have our baseline absolute values sitting right next to the turbine absolute values. But wait, we don't stop there. We also include the relative delta, that percentage change, and finally, a mechanism column. Having absolute values anchored right next to relative changes and then supporting that with a technical mechanism, that paints a complete, totally unassailable picture of exactly what happened. And visually, I mean, the jump is just undeniable. Our baseline throughput is chugging along at, say, 120 megabytes per second. But then, the turbine-enabled integration rockets up to 178 megabytes per second. Suddenly, all those abstract numbers in the CSV files feel very, very real. This massive leap in sustained throughput is immediate, and it's crystal clear. To put that into perspective, that jump translates to a massive plus 48% relative lift. 48%! This is exactly the kind of energy and practical, real-world impact that stakeholders and technical reviewers actually care about. Getting a 48% increase in capacity without having to upgrade the physical hardware, that's a huge win. But again, it only really matters if you can decisively prove it. But remember, numbers mean absolutely nothing without the why. And that brings us right back to that mechanism column in our table. Think about it. If we observe a drop in per-node peak bandwidth under Turbine, but our overall throughput actually went up, what does that tell us? Well, it proves that Turbine's multicast chunking is successfully distributing the load across the network way better than the baseline fanout. Mapping your metric directly to a technical mechanism, that is the secret sauce. That's what transforms a basic measurement into a verifiable, hard-hitting engineering claim. We also need to visualize variability, like we do with this latency distribution chart. You see, point estimates, like just giving a single median average, they can hide a lot of sins. But by plotting latency distributions, like cumulative distribution functions, we prove to our audience that our gains are actually robust. If 85% of our messages are delivered well under the target median and 95% are inside an acceptable boundary, it shows that our throughput gain wasn't just some statistical fluke or transient noise. It proves we've got a stable, highly performant system. And that brings us to our final section, Section 5, 3 rules for proof. Think of this as the engineer's oath. So consider this your engineer's oath as we wrap up this explainer. I really want you to have these 3 rules perfectly memorized, like a blueprint etched in your brain. Rule 1, normalize before you compare. Always use those steady-state windows and convert to like-for-like units. Rule 2, surface variability. Do not hide it. Show your confidence intervals and distribution plots so people know your gains aren't just random noise. And Rule 3, connect every single metric to a technical mechanism. Pair every measured improvement with the exact log evidence or integration patch that actually caused it. So what does this all mean? Well, you've cleaned up the messy receipts, you've run your Python workflow, and you've generated some seriously indisputable charts. You've built the evidence. But here's the real question. How will you weave these visual charts into a comprehensive narrative that perfectly proves Turbine's optimization? Well, that is exactly what we're going to tackle in our final capstone assembly explainer. Before we go, I highly encourage you to head over to Forge College to explore more of our advanced programs, dive deeper into this subject, and master even more Web3 topics. This explainer was brought to you by Forge College. I'll see you in the assembly phase. Let's keep building.